A massive structure surrounding a star to harness. All its energy, could this be the key for civilizations to conquer the universe? The Dyson Sphere is one of the most audacious ideas in astrophysics and the study of extraterrestrial civilizations. With the potential to capture all the energy emitted by a star, this structure not only opens doors for Type II civilizations on the Kardashev scale, but also provides intriguing hypotheses about advanced life signs in the universe. 1. Dyson Sphere. Concept and challenges. The concept of a Dyson sphere, first proposed by physicist Freeman Dyson in 1960, stands as one of the boldest and most fascinating ideas in astronomy and space technology. In his scientific paper, Dyson envisioned how an advanced civilization might optimize energy extraction from their star by constructing a massive system around it. This system, commonly referred to as the Dyson Sphere, is not a singular structure, but rather a network of satellites or energy-collecting panels designed to capture and utilize all the energy emitted by the star. The Dyson Sphere is considered a monumental step forward in solving the energy demands of advanced civilizations. As civilizations grow, their energy needs exceed what their home planet can provide. Harnessing the total energy of a star would become an almost inexhaustible resource, enabling not only survival, but also expansion and development on a galactic scale. This idea offers not just a theoretical solution to energy problems, but also a vital method for detecting alien civilizations. If a Dyson Sphere exists, it might leave observable traces, such as unusual dimming of a star's brightness or distinctive thermal radiation signatures. However, constructing a Dyson Sphere poses immense technical challenges, requiring technology and resources far beyond human capability today. The satellites or panels must withstand the star's extreme temperatures while maintaining precise orbital alignment to avoid collisions or instability. Managing the stability of the entire system raises numerous questions about materials, energy, and governance. Still, for a Type II civilization on the Kardashev scale, building a Dyson Sphere might be within reach, marking a pivotal moment in their evolutionary trajectory. Beyond technical aspects, the Dyson Sphere raises ethical and existential questions about survival in the universe. A civilization constructing a Dyson Sphere would not merely harvest energy, but fundamentally alter the environment around their star. This could impact nearby planetary systems or other civilizations, if present. It also serves as a reminder of the responsibility humanity bears as it pursues ambitious space ventures. The concept of the Dyson Sphere extends beyond science fiction, offering hope for future exploration and development. Although we are far from achieving such a feat, studying and imagining it stimulates scientific and technological progress. For scientists, the Dyson Sphere is not merely a symbol of extraordinary advancement, but also one of the most promising tools for exploring the universe, seeking signs of intelligent life, and broadening humanity's perspective on its existence within the vast cosmos. Potential applications of the Dyson Sphere. If an advanced civilization succeeds in building a Dyson Sphere, they would gain access to an almost limitless energy source, enabling possibilities far beyond what we can currently envision. This immense energy reservoir would become the driving force behind maintaining and expanding the civilization, powering artificial ecosystems, space stations, and even large-scale space projects, such as exploring and colonizing other star systems. One notable application of the Dyson Sphere is supplying energy for interstellar spacecraft. With abundant energy, spacecraft could employ advanced technologies such as antimatter engines, light sails, or fusion drives, achieving high speeds and optimal efficiency. This would not only allow the civilization to extend its presence beyond its home star system, but also facilitate exploration of distant galaxies and the establishment of bases in alien regions of space. In addition to exploration, the Dyson Sphere could provide effective remote energy solutions. Energy harnessed from the star could be converted into laser beams or radio waves and transmitted to planets, space stations, or spacecraft. This approach would solve the problem of energy supply in locations where direct sunlight or natural resources are unavailable. For example, a distant planet in the shadow of its star could still receive energy through advanced transmission systems from the Dyson Sphere. The energy harnessed by the Dyson Sphere could also enable the construction of large-scale artificial environments, where conditions like temperature, lighting, and climate are perfectly controlled. These environments could not only support space colonization, but also serve as solutions to climate and ecological challenges on the civilization's home planet. If the civilization faced severe climate change or environmental degradation, using energy from the Dyson Sphere to regulate the climate or build sustainable living habitats would become a critical lifeline. Moreover, this energy source could support scientific and technological megaprojects. The civilization could conduct physics experiments beyond current limits, such as creating high-energy particles to study the structure of the universe or simulating conditions during the early stages of the Big Bang. These studies would not only expand knowledge, but also foster the development of new technologies to sustain continuous advancement. The Dyson Sphere represents more than a technological milestone. It is a key to achieving comprehensive energy autonomy. It not only ensures the civilization's survival, but also paves the way for prosperity and expansion across the universe. While still a theoretical concept today, realizing the Dyson Sphere would mark a historic turning point in any civilization's evolutionary journey. Detecting a Dyson Sphere. Discovering a Dyson Sphere, if it exists, would be one of the most compelling pieces of evidence for the presence of advanced extraterrestrial civilizations. A critical indicator of such a structure would be the unusual dimming of a star's emitted light. When a star is surrounded by a system like the Dyson Sphere, part of its light would be blocked, resulting in irregular brightness decreases, an observable phenomenon with modern telescopes. One prominent case that has captured the scientific community's attention is Tabby's star, KIC 8462852. Located approximately 1,470 light-years from Earth, this star has exhibited unexplained variations in brightness that deviate from stable cyclical patterns. Sudden dimming events, sometimes reaching up to 22%, have led researchers to propose numerous hypotheses, including the possibility of a Dyson Sphere encircling the star. While natural explanations, such as the presence of a massive dust cloud or debris from a disintegrated planet, remain more plausible, Tabby's star has sparked renewed interest in searching for artificial structures in space. In addition to dimming phenomena, another hallmark of a Dyson Sphere is thermal radiation emission in the form of infrared light. When energy from a star is captured by the Dyson Sphere, not all of it is used efficiently. Some is dissipated as heat, creating an abnormal infrared emission detectable by modern instruments. This is one of the primary objectives of infrared telescopes, like WISE, Wide Field Infrared Survey Explorer. WISE scans millions of stars across the galaxy, seeking those with thermal characteristics inconsistent with natural processes. Although several intriguing discoveries have been made, no definitive evidence of a Dyson Sphere has been found to date. Furthermore, cosmic simulations suggest that a Dyson Sphere might leave other indirect clues, such as changes in the spectral properties of the star's light or minor perturbations in the orbits of nearby celestial bodies. These subtle signals could become vital leads if we develop the means to analyze astronomical data more effectively. Research initiatives like SETI are expanding their scope from traditional radio signals to anomalies in light and thermal patterns of stars, increasing the likelihood of identifying signs of advanced civilizations. Although no concrete evidence of a Dyson sphere has yet emerged, current studies have opened new doors in the search for extraterrestrial intelligence. Cases like Tabby's star, or stars with unusual infrared emissions, not only fuel curiosity, but also drive advancements in observational and analytical technologies in astronomy. Should we one day uncover clear evidence, it would not only confirm the existence of an advanced civilization, but also fundamentally alter how we perceive our place within the vast universe. If millions of light-years could be traversed in seconds, could wormholes unlock a new era of galactic exploration? Wormholes, a captivating theoretical phenomenon from Einstein's general theory of relativity, have inspired not only science, but also works of fiction. With their potential to connect distant points in space-time, wormholes could provide a solution to traversing vast cosmic distances, if they truly exist. The concept and mechanics of wormholes. Wormholes, also known as Einstein-Rosen bridges, are a prominent theoretical concept in physics, predicted by Albert Einstein and Nathan Rosen through the general theory of relativity. According to this theory, wormholes are tunnels in space-time that connect two distant points. If they exist, they could serve as bridges enabling instantaneous travel from one point to another in the universe. This idea resembles teleportation, but is grounded in physical principles rather than pure science fiction. A wormhole structure consists of two mouths located at different points in space-time, linked by a throat. The theory suggests that if a wormhole could be created and stabilized, it would significantly shorten travel time and distance. For example, instead of taking millions of light-years to travel between star systems, passing through a wormhole could occur in mere moments. This opens unprecedented possibilities for interstellar travel, space exploration, and even communication between extraterrestrial civilizations. However, the functioning of wormholes is far from simple. Calculations in general relativity indicate that gravity would cause a wormhole to collapse instantly upon formation unless a type of exotic matter exists to stabilize it. This exotic matter is theorized to possess negative energy, a concept yet to be experimentally verified by modern science. Such matter would not only play a crucial role in maintaining the wormhole's stability, but would also need to counteract gravitational forces and other dynamic effects. Beyond the physical challenges, visualizing and utilizing wormholes raise numerous scientific and philosophical questions. Can humans create or harness a wormhole? What would be the causal implications of passing through one? And would traveling through a wormhole be safe, or could it lead to the destruction of objects passing through it? These unanswered questions add to the intrigue and mystery surrounding this concept. Although no experimental evidence currently confirms the existence of wormholes, the concept has paved new avenues in theoretical physics and cosmology. Scientists continue to explore the potential of emerging theories, such as string theory or quantum gravity, to better understand how wormholes might exist and operate. Simultaneously, future technologies may offer breakthroughs in testing this theory. Wormholes are not merely ambitious ideas in physics, but also significant sources of inspiration in popular culture, from science fiction novels to blockbuster films about space travel. While distant from practical reality, studying wormholes has shaped how we perceive the universe, a place of boundless expansion, mysteries, and possibilities. If humans can one day prove and exploit wormholes, it would revolutionize our understanding of time and space, as well as how we traverse them. Challenges in realizing wormholes. Although wormholes are a promising concept for interstellar travel, Realizing them faces numerous scientific and technological complexities. First, the existence of wormholes is purely theoretical, based on equations from general relativity, with no experimental evidence to confirm them. While theoretically plausible, proving their existence or creating them remains beyond the current capabilities of science. One of the greatest hurdles is exotic matter, which is essential for stabilizing wormholes. This matter must have negative energy to counteract gravitational forces, preventing the wormhole from collapsing immediately after formation. However, while negative energy is referenced in some quantum physics theories, it has yet to be directly observed or proven. Even if an advanced civilization could discover a method to produce exotic matter, generating sufficient quantities to maintain a wormhole large enough for spacecraft remains a colossal challenge. Additionally, the safety of using wormholes poses significant concerns. Objects passing through a wormhole, such as spacecraft or particles, could generate radiation or gravitational forces that destabilize the wormhole's structure. As a result, the wormhole might collapse during use, posing severe risks to any beings or equipment traveling through it. Furthermore, interactions between the wormhole and its surroundings, such as cosmic radiation or other gravitational fields, could complicate its stability. The challenges are not limited to theoretical physics, but also involve the development of suitable technologies to manipulate wormholes. To test or harness a wormhole, humanity would need measurement and control tools capable of managing gravitational forces with unprecedented precision. This would require groundbreaking advances in particle physics, quantum mechanics, and space engineering, fields still in their early stages of development. Nevertheless, despite these significant obstacles, wormholes remain a highly intriguing and promising area of research. Scientists continue to search for signs of wormholes in the universe, such as distortions in space-time or unexplained astronomical phenomena. Advanced theoretical models, including string theory and loop quantum gravity, are opening new approaches to understanding and addressing wormhole-related challenges. If humanity can one day overcome these barriers, exploiting wormholes would mark a historic milestone, enabling us to explore the universe further than ever before. Although the concept remains theoretical, it has profoundly inspired both science and popular culture, envisioning a future where the limits of space and time may be transcended. Wormholes and the future of interstellar civilizations. If an advanced civilization could harness wormholes, they would possess a revolutionary tool with the potential to transform travel, communication, and research in the universe. Wormholes, theoretically, could link distant regions of space-time, offering applications far beyond humanity's current limitations. One of the most remarkable uses of wormholes would be instantaneous travel between star systems or even galaxies. While reaching neighboring star systems now requires thousands of years, wormholes could reduce such journeys to mere seconds or minutes. This capability would facilitate the exploration of distant planets and open opportunities for settlement on new worlds with life-sustaining potential. Journeys once deemed impossible would become practical, enabling civilizations not just to survive, but to expand their influence across the cosmos. Beyond travel, wormholes could revolutionize information and material transmission. A network of wormholes established between planets or star systems could function as cosmic highways for data and resources. This would allow civilizations to exchange information almost instantaneously, surpassing the speed of light's constraints. Spacecraft embarking on long-term missions would no longer need to carry all necessary supplies, as wormholes could serve as remote supply hubs, conserving energy and resources. In emergencies, civilizations could use wormholes to deliver technology, materials, or medical aid anywhere in the network. Wormholes also offer unprecedented opportunities in scientific research. With immediate access to distant regions of the universe, scientists could conduct direct studies in areas currently observable only from afar. These might include phenomena like supernovae, black holes, or even remote celestial bodies in other galaxies. If wormholes indeed connect to other dimensions, they could unveil entirely new realms of understanding about the universe, including theories on multiverses and higher dimensions. Moreover, wormholes could support practical applications in building and maintaining space habitats. Advanced civilizations might use wormholes to link space stations or settlements on different planets, creating a tightly interconnected cosmic ecosystem. This capability is particularly significant for civilizations relying on resources from multiple planets or needing to maintain interaction between distant colonies. While still a theoretical concept, wormholes promise unparalleled advancements, not only driving the development of civilizations, but also fundamentally altering how we perceive and interact with the universe. If one day humanity or another civilization overcomes the scientific and technological barriers to exploiting wormholes, the doors to humanity's greatest dreams of space exploration will open. From discovering new worlds to forging intergalactic connections, wormholes would be more than a tool for transportation. They would be the key to evolving and thriving in an expansive and enigmatic universe. Imagine a colossal megastructure in space, where millions of beings live and work, self-sustained like a compact world amidst the vast cosmos. This is the McKendree Cylinder, a bold and ambitious dream of humanity. The McKendree Cylinder, a prominent concept in science fiction and space engineering, presents a vision of massive space structures where humans could survive, thrive, and explore the universe. Based on advanced physical and engineering principles, the McKendree Cylinder holds the potential to become an ideal habitation model for the future. The ambitious concept of the McKendree Cylinder. The McKendree Cylinder is an audacious concept, describing a massive space structure far surpassing anything humans have built on Earth. Stretching thousands of kilometers in length and wide enough to house a large city, the McKendree Cylinder embodies cutting-edge technology and boundless imagination. This enormous size necessitates the use of ultra-strong materials like carbon nanotubes, one of the lightest yet strongest materials known to date. These materials must withstand the pressures of space, including radiation, micrometeorite impacts, and extreme temperature fluctuations, while maintaining the structure's stability in a microgravity environment. The most notable feature of the McKendree Cylinder is its ability to spin on its axis to generate artificial gravity. The centrifugal force created by this rotation simulates Earth-like gravity, enabling inhabitants to maintain health and normal functioning. This is a crucial solution to the health problems humans often face in zero-gravity environments, such as bone density loss, muscle atrophy, or other physiological disorders. Inside the cylinder, modular layers are designed to provide diverse and flexible living spaces, including residential areas, agriculture, industrial production, scientific research, and recreational zones. Self-sustainability is a core element of the McKendree Cylinder, transforming it into not just a habitation, but a self-contained society. Waste recycling, energy management, and resource conservation systems ensure the cylinder can operate continuously without heavy reliance on external supplies. For instance, energy could be harvested from massive solar panels installed around the structure, or from advanced fusion reactors. Food supplies could be maintained through hydroponic and aeroponic agricultural zones within the cylinder, where crops are nurtured using optimized water and nutrient systems. Beyond habitation, the McKendree Cylinder has the potential to serve as a hub for high-tech research and production. The unique environment of space allows experiments that are difficult or impossible to conduct on Earth. The cylinder could function as a giant laboratory for research in physics, medicine, and materials science. Additionally, access to resources from nearby celestial bodies, such as asteroid mining, could provide abundant raw materials for manufacturing within the cylinder. With the capacity to accommodate millions of residents, the McKendree cylinder becomes a complete society, equipped with all systems necessary for life and development. It is not just a place to live, but a significant step toward shaping humanity's future beyond Earth. Population management, social organization, and economic models within the cylinder would need to be designed for efficiency and sustainability, ensuring a harmonious living environment for all residents. Each layer of the cylinder could be customized to serve specific purposes, from education and healthcare to public and cultural spaces. The McKendree cylinder is not merely a technological dream, but also a symbol of humanity's ambition to conquer space and adapt to its challenges. Though currently theoretical, this concept is the starting point for larger ideas about constructing societies beyond Earth. With ongoing advancements in materials science, energy technology, and environmental management, the McKendree cylinder could become a reality in the future, marking a milestone in humanity's journey to expand beyond its home planetary system. The McKendree cylinder as a catalyst for space exploration. The McKendree cylinder is more than a massive residence. It is an essential component in the strategy to explore space and expand human presence beyond the solar system. As humanity looks toward distant planetary systems, constructing megastructures like the McKendree cylinder becomes a necessary solution for creating long-term space bases that ensure sustainable survival and development in the harsh environments of space. One of the most crucial applications of the McKendree cylinder is to provide a self-sustaining living environment for large populations. Internal systems would be designed to be entirely closed-loop, including zones dedicated to agriculture, livestock, and food production. Advanced technologies like hydroponics and aeroponics would be employed to grow crops and produce food in limited space, minimizing reliance on supplies from Earth. Simultaneously, modern water and air recycling systems would ensure resources are used efficiently and continuously, meeting all basic living needs for inhabitants. The McKendree cylinder could also function as a strategic way station in interstellar journeys. As humans embark on missions to explore or colonize distant planetary systems, the cylinder would serve as a critical stopover point. Smaller spacecraft could utilize the McKendree cylinder to refuel, undergo repairs, or prepare for longer journeys. With its large storage capacity, the cylinder could also act as a warehouse and distribution hub, supporting other space bases or supplying equipment for extraterrestrial missions. Moreover, the McKendree cylinder offers an effective alternative for habitation, particularly as planets like Mars or Europa remain under study for their potential to support life. Instead of relying on unstable natural conditions or limited resources, the cylinder enables humans to create a fully controlled living environment. Inside, factors like temperature, pressure, and radiation could be regulated to maintain optimal conditions for life. This not only facilitates human adaptation to space, but also opens the possibility of settling in regions without atmospheres or resources sufficient to sustain life, such as asteroids or distant icy moons. Beyond supporting habitation, the McKendree cylinder could serve as a vital center for research and manufacturing. The unique conditions of space would allow for experiments and the production of materials that are impossible on Earth. For instance, advanced compounds or medical experiments requiring microgravity could be conducted within the cylinder. Additionally, it would be an ideal location for deploying astronomical observation devices, aiding scientists in studying distant cosmic phenomena or collecting data from hard-to-reach areas of the universe. Ultimately, the McKendree cylinder is not merely an infrastructure project, but a testament to humanity's adaptability and ingenuity. By integrating advanced technologies and functioning as a self-contained society, the cylinder represents a significant leap in shaping the future of human life in space. More than just a residence or transit hub, the McKendree cylinder bridges the gap between the present and a future where humanity can conquer the furthest frontiers of space. With continuous advancements in science and technology, the vision of the McKendree cylinder is no longer just a dream, but a step toward reality in humanity's expansive exploration of the cosmos. Challenges in realizing the McKendree cylinder. Building the McKendree cylinder, a massive space megastructure, is an ambitious idea fraught with significant challenges in engineering, technology, finances, and politics. One of the most critical obstacles is construction materials. Traditional Earth-based materials, including steel and advanced alloys, cannot meet the requirements for strength and lightness needed to withstand the pressures of the McKendree cylinder's immense size and the harsh conditions of space. This necessitates the development of new materials, such as carbon nanotubes or graphene, which are hundreds of times stronger than steel, while being extremely lightweight. However, producing these materials on a large scale and at reasonable costs remains a significant challenge for modern science. The second challenge lies in transporting and assembling the cylinder's components in space. Given its massive size, the cylinder cannot be fully constructed on Earth and launched into space. Instead, its components would need to be manufactured, transported, and assembled directly in orbit. This requires close coordination of advanced robotic systems, space-based 3D printing technology, and complex automation solutions to ensure precise and safe assembly. While these technologies have made notable progress, they are still in the developmental stage and not yet mature enough for a project of this scale. Beyond physical construction, providing energy to operate the entire system within the McKendree cylinder poses another major challenge. The enormous energy demands for maintaining lighting, temperature, life support systems, and the activities of its inhabitants would necessitate reliance on renewable energy sources like solar power. However, collecting and efficiently distributing energy on such a large scale would require unprecedented technologies. Additionally, if the McKendree cylinder is located in distant star systems, it would need to incorporate solutions to directly harness energy from those stars, introducing even more complex technical requirements. Another critical issue is maintaining a closed-loop ecosystem within the cylinder. The McKendree cylinder would require a self-sustaining ecological system capable of functioning for decades or even centuries, providing basic necessities like food, water, and air for millions of residents. This demands the development of natural and sustainable recycling systems such as space-based agriculture, water and air recycling, and advanced waste management technologies. Scientists must address not only maintaining ecological balance, but also ensuring these systems operate reliably without frequent external intervention. Challenges extend beyond technical hurdles to include financial and political barriers. Building a megastructure of this scale demands enormous funding, far exceeding the capabilities of any single nation. This necessitates international collaboration, not only to share costs, but also to leverage resources and expertise from multiple countries. However, global cooperation on such a scale is not easily achieved, especially considering the diverse economic and political interests of nations. Whether humanity is willing to prioritize long-term investment in such a challenging project remains an open question. In conclusion, while the McKendree cylinder offers hope for a sustainable spacefaring future and deep space exploration, realizing this idea requires monumental advancements in technology, massive financial investment, and unprecedented global consensus. It is not just a test of science and engineering, but also a significant challenge to humanity's unity and vision in addressing large-scale cosmic endeavors. The most powerful energy source ever known. Could the antimatter engine turn the dream of intergalactic travel into reality? The antimatter engine is regarded as one of the boldest concepts in physics and space engineering. With the potential to generate energy from the complete annihilation of matter and antimatter, this technology promises near-light-speed travel, ushering in a new era of exploration and conquest of the cosmos. Antimatter engines, revolutionary potential in space travel. The antimatter engine is a revolutionary concept in space travel technology, based on a fundamental phenomenon in particle physics: the annihilation of matter and antimatter. When a particle of matter, such as a proton, meets its corresponding antiparticle, such as an antiproton, both annihilate each other and release tremendous amounts of energy in the form of gamma rays. This is one of the most powerful reactions in nature, capable of producing energy far surpassing any current chemical or nuclear fusion sources. The annihilation reaction follows Albert Einstein's famous equation E = mc squared, where the total mass of both matter and antimatter is fully converted into energy. This exceptional efficiency makes antimatter an ideal energy source. For example, just 1 gram of antimatter could produce energy equivalent to 23,000 tons of TNT, enough to power a spacecraft for a long journey through space without requiring massive fuel tanks like current propulsion systems. This is particularly critical for interstellar missions, where distances between planets or star systems span millions or even billions of light years. The working principle of an antimatter engine involves controlling and converting the energy released from annihilation into thrust. One proposed method is to use the emitted energy to heat plasma or generate charged particle streams. Plasma, at extremely high temperatures, could be expelled through a specialized nozzle at tremendous speeds, producing powerful thrust to propel the spacecraft. Similarly, charged particle streams could be directed by magnetic fields to create controlled thrust, optimizing energy use. Thanks to its ability to generate high-efficiency thrust, the antimatter engine has the potential to enable spacecraft to achieve extremely high speeds, possibly close to the speed of light. This capability not only makes interstellar journeys feasible within shorter timescales, but also significantly reduces challenges related to fuel supply and long-term travel durations in space. For instance, a journey to the nearest star, Proxima Centauri, over 4.24 light-years away, could be shortened from thousands of years with current technology to just a few decades with an antimatter engine. However, deploying antimatter engines comes with significant challenges. Producing, storing, and controlling antimatter safely are complex scientific and engineering problems that remain unsolved. Antimatter annihilates upon contact with any ordinary matter, necessitating advanced storage devices that use strong magnetic fields to isolate antimatter in a vacuum. Furthermore, the cost of antimatter production is currently exorbitant, with each gram potentially costing millions of dollars. Despite these hurdles, the antimatter engine remains one of the most intensely researched and developed technologies. If current barriers can be overcome, antimatter propulsion could not only break humanity's distance limitations in space, but also inaugurate a new age of discovery, where distant star systems and planets are no longer out of reach. This is not just a science fiction dream, but a driving force for scientific and technological advancement in the future. Transformative applications of antimatter engines. If realized, the antimatter engine would mark a revolutionary leap, heralding a new era for interstellar and intergalactic travel. This technology, with its unparalleled energy output and efficiency, has the potential to help humanity transcend current limitations, turning the exploration of deep space into a tangible reality. One of the most remarkable benefits of antimatter engines is their ability to drastically increase travel speeds in space. Currently, spacecraft using chemical or ion propulsion require decades to reach distant planets within the solar system, such as Neptune or Pluto. With antimatter engines, spacecraft could achieve speeds nearing the speed of light, reducing such journeys to just weeks or months. This would not only make solar system exploration more feasible in shorter timeframes, but also unlock access to nearby star systems. For instance, a journey to Proxima Centauri, currently taking thousands of years with existing technology, could be completed in mere decades with antimatter propulsion. Beyond transportation, antimatter engines could support the construction and maintenance of self-sustaining space bases. With the ability to provide stable and long-lasting energy, this technology could supply the necessary power for bases on distant celestial bodies, such as Mars, Europa, or Titan. These bases would no longer need to rely on Earth for supplies, significantly reducing costs and increasing self-sufficiency. This is particularly crucial for long-term missions or space resource extraction efforts, where humans must operate in harsh and remote environments. Antimatter engines also offer immense value in advancing large-scale scientific exploration projects. With superior speeds, spacecraft equipped with such engines could rapidly reach enigmatic cosmic phenomena like black holes, supernovae, or regions with extreme conditions yet to be explored. Gathering data from these regions would provide humanity with deeper insights into the nature of the universe, from galaxy formation to extraordinary physical phenomena beyond current understanding. Additionally, antimatter engines could power mobile research stations or space observatories. These stations, strategically positioned across the cosmos, could monitor and study significant cosmic events in real time. With powerful energy sources, scientific instruments on these stations would operate continuously and efficiently, enabling unprecedented research opportunities. Furthermore, antimatter engines could facilitate the development of interplanetary or interstellar energy transmission technologies. By converting antimatter energy into transmittable forms, advanced civilizations could establish energy networks between space bases or even between planets. This would not only ensure sustainable development for extraterrestrial civilizations, but also enhance communication and collaboration across the cosmos. While the development and deployment of antimatter engines are far from simple, the extraordinary advantages of this technology make it a strategic investment for humanity's quest to conquer space. Someday, antimatter engines might underpin every journey into the cosmos, heralding a new era of human development and evolution. Challenges and opportunities in antimatter engine development. Developing antimatter engines brings hope for a new era of space travel, but it also comes with immense technical and technological challenges. One of the greatest obstacles is the production of antimatter. This powerful energy source is not only difficult to create, but also prohibitively expensive. Currently, antimatter can only be produced in advanced research facilities like CERN, using high-energy particle accelerators. However, the quantities of antimatter generated are minuscule, and production costs are astronomical. Estimates suggest that producing just 1 gram of antimatter could cost millions of dollars, far exceeding the financial capacity of any single organization or nation. Storage of antimatter presents another significant challenge. Antimatter has a unique property. It annihilates upon contact with ordinary matter, releasing an immense energy burst. To store antimatter safely, scientists have explored using magnetic traps to suspend antimatter particles in a vacuum, preventing contact with material surfaces. However, magnetic trap technology is currently in its experimental stages and has yet to be scaled for practical applications such as operating spacecraft. In addition to storage, controlling the energy released from matter-antimatter annihilation is a daunting task. Each reaction releases colossal energy per Einstein's equation, E equals mc squared, and without precise control, the consequences could be catastrophic. A minor malfunction in operating an antimatter engine could cause an explosion large enough to destroy not only the spacecraft, but also pose significant risks to the surrounding environment. Advanced safety systems and continuous monitoring measures would be required to ensure stable operation throughout any journey. Financial constraints add to the complexity. Developing antimatter engines demands massive investments in fundamental research, advanced production facilities, and technology testing. These costs far exceed current space agency budgets, necessitating international collaboration and the involvement of various organizations, both public and private. Such investments not only require funding, but also decades of research to achieve necessary breakthroughs. The complexity of antimatter engines also raises questions about their practical feasibility. Can humanity achieve sufficient control and optimization to safely and effectively apply this technology to space travel? And do the benefits of antimatter engines outweigh the colossal costs and risks involved? Despite these challenges, the prospects offered by antimatter engines remain compelling. With unparalleled energy capabilities, this technology could revolutionize the way humans travel and explore the cosmos. If obstacles in production, storage, and operation can be overcome, antimatter engines will not only mark a scientific and technological milestone, but also unlock a future where humanity reaches beyond its current limits. They will enable us to explore distant star systems and provide a foundation for delving deeper into the universe, unraveling mysteries about its origins and our destiny. When planetary surfaces become uninhabitable, can we construct floating cities in the skies where science and life intertwine? The concept of floating cities in planetary atmospheres stands as one of humanity's most innovative solutions to overcoming harsh environmental barriers. These cities not only offer an answer to survival on planets with uninhabitable surfaces, but also promise opportunities for resource extraction and the exploration of new frontiers. Floating cities, a visionary solution for harsh planetary environments. Floating cities represent an ambitious idea to create habitable environments on planets where surface conditions are unsuitable for human life. Instead of relying on solid ground like traditional urban areas, floating cities would be designed to hover in atmospheres using advanced technologies. One viable method involves employing gases lighter than air, such as hydrogen or helium, to maintain altitude. Additionally, modern propulsion systems could be integrated to keep the cities stable in desired locations, even amid turbulent atmospheric conditions. This concept is particularly suited to planets with dense atmospheres where pressure or temperature varies with altitude. A prominent example is Venus, whose surface is often described as a hellscape, with temperatures exceeding 900 degrees Fahrenheit, 475 degrees Celsius, and pressure 90 times that of Earth. While Venus's surface is uninhabitable, at an altitude of approximately 50 kilometers, temperatures and pressures decrease to relatively stable levels, providing a feasible environment for floating cities. At this altitude, the predominantly carbon dioxide CO2 atmosphere can even act as a natural buoyant medium, as it is denser than gases like oxygen, nitrogen, or hydrogen mixtures. Floating cities would not only serve as residential hubs, but also incorporate advanced technologies to ensure self-sustainability. Renewable energy systems, such as solar panels, could harness sunlight or high planetary temperatures to power devices. Air and water would be processed and recycled through closed-loop systems, ensuring maximum reuse of resources and reducing dependency on external supplies. Additionally, atmospheric filtration systems could transform planetary gases into valuable resources. The structural design of floating cities would require cutting-edge materials that are both lightweight to minimize load and durable to withstand extreme environmental conditions. Advanced alloys, carbon fibers, or ultra-light composites would be employed to construct living spaces, work zones, and operational systems. These areas would provide not only residential and workspaces, but also zones for agriculture, scientific research, and industrial production, transforming floating cities into closed-loop ecosystems capable of long-term self-sufficiency. Beyond Venus, the concept of floating cities could also be applied to other planets or moons in the solar system, where surfaces are inhospitable but atmospheres offer favorable conditions. For instance, the upper atmospheres of Jupiter or Saturn, where pressure and temperature levels are more tolerable, could become potential targets for similar projects. In the future, floating cities might even connect via interstellar corridors or transit stations, forming a network that fosters communication and collaboration among extraterrestrial settlements. The idea of floating cities is not only a groundbreaking solution for hostile environments, but also a significant step forward in humanity's exploration and colonization of space. It embodies our capacity to transcend current limitations, transforming previously deemed impossible places into thriving centers of life and development. If successful, these cities would not only expand humanity's reach into the cosmos, but also provide a sustainable and innovative model for living, even in the harshest environments. Venus, a prime candidate for floating cities. Venus, a planet similar in size and composition to Earth, has long been regarded as a compelling target for floating city deployment. A revolutionary concept in space exploration and extraterrestrial settlement. While Venus's surface is uninhabitable due to its extreme temperatures, reaching up to 475 degrees Celsius, and atmospheric pressure 90 times greater than Earth's, the atmospheric layer at about 50 kilometers altitude provides a relatively mild environment. Here, temperatures hover around 30 degrees Celsius, and pressure is comparable to sea level on Earth, making it one of the most viable extraterrestrial environments for sustainable habitation. Floating cities on Venus could operate as self-sustaining ecosystems, leveraging abundant resources from the CO2-rich atmosphere. Advanced technologies such as artificial photosynthesis or chemical reactions could convert CO2 into oxygen, supplying breathable air for inhabitants. At the same time, the intense sunlight on Venus could serve as a robust energy source, harnessed through high-efficiency solar panels. This renewable energy could power life support systems, from air conditioning and water processing to food production. In addition to being residential hubs, floating cities on Venus could become pioneering centers for scientific research. With scientists and engineers stationed in these cities, studies could delve into extreme climates, atmospheric chemistry, and planetary evolution. Such research would not only deepen our understanding of Venus, but also provide insights into the harsh environmental conditions across the solar system and how planets, including Earth, might evolve in the future. Moreover, Venus offers an ideal setting for testing technologies to extract resources from the atmosphere. In addition to CO2, its atmosphere contains nitrogen and trace amounts of water vapor. Innovative technologies could be developed to harvest water from the atmosphere, which could then be used for living purposes or as raw material for other chemical reactions. The ability to utilize in-situ resources would reduce reliance on supplies from Earth, cutting costs and increasing the sustainability of extraterrestrial settlement projects. Beyond scientific and technological benefits, floating cities on Venus could also serve as transit hubs for deeper space exploration missions. From Venus, humanity could develop technologies and protocols for settling in extreme atmospheric conditions, which could then be applied to more challenging environments like Mars, Europa, or other distant celestial bodies. Successfully building and operating a floating city on Venus would mark a monumental milestone in humanity's journey to conquer space. Floating cities on Venus not only exemplify the potential to overcome the limits of science and engineering, but also showcase humanity's adaptability and creativity. If realized, these cities would expand the boundaries of human habitation in the cosmos, while providing invaluable knowledge to address challenges on Earth and beyond in the vastness of space. Beyond Venus, floating cities on gas giants and exoplanets. The idea of floating cities is not confined to Venus. It also holds promise for deployment on gas giants such as Jupiter, Saturn, or even exoplanets in distant star systems. While these planets lack solid surfaces, their dense atmospheres rich in useful compounds offer significant opportunities to establish research bases or resource extraction hubs in space. Jupiter, the largest planet in the solar system, has an atmosphere abundant in hydrogen and helium, two key elements for generating energy and fuel for space travel. Floating cities on Jupiter could act as transit stations or refueling bases, providing ample energy resources for deep space missions. These cities could also serve as research hubs to study Jupiter's atmosphere and powerful magnetic fields, offering valuable insights into gas giant planets and related physical phenomena. Similarly, Saturn, with an atmosphere containing methane and other organic compounds, could host floating cities that serve as centers for studying prebiotic chemistry. Such research could deepen our understanding of how life might form and evolve in diverse environments. Additionally, these facilities could extract resources to support other space bases within the solar system, expanding humanity's operational reach. Beyond the solar system, the floating city concept has potential applications on exoplanets with thick atmospheres. Advanced observational tools like the James Webb Space Telescope are helping scientists identify distant planets with conditions conducive to deploying floating structures. These planets could become not only sites for scientific research, but also potential long-term settlements in the distant future. Floating cities on exoplanets would pave the way for sustainable space bases in the universe. These cities could be designed to utilize local resources, minimizing dependency on Earth. Moreover, they would enable the study of astronomical phenomena and extend humanity's presence beyond the solar system. In addition to research and resource extraction, floating cities could function as intermediary bases for deep space exploration. Spacecraft could use them as pit stops for refueling, maintenance, or technical preparations for long-duration missions. This would optimize costs and timelines for space missions while reducing risks for crews operating far from Earth. The benefits of floating cities extend beyond science and technology. They also hold strategic value. Successfully deploying such cities would mark a major milestone in humanity's journey to conquer space, heralding a new era where humans not only explore, but also live and work on distant worlds. This vision reflects not only ambition, but also humanity's boundless adaptability and creativity.